Hi, this is Sujita presenting a topic on Advanced Encryption Standard, that is AES. The AES origins, that is, it is we used to use uh, DES before for the encryption and decryption in the cryptography, but we need some replacement for DES because we have some theoretical attacks that can be break it, and we also have some demonstrated exhaustive key search attack. So we can use the triple DES, but that is very slow, what we found, and also have small box. So we need some replacement. That is what we got, the advanced encryption standard. This advanced encryption standard, it was published by NIST, that is National Institute of Standards and Technology, in 1997. This AES is a symmetric block cipher that is intended to replace DES as the approved standard for a wide range of applications. The AES cipher form the latest generation of block ciphers, and now we see a significant increase in the block size from the old standard of 64 bits up to 128 bits, and keys from 128 to 256 bits. In part, this has been driven by the public demonstrations of exhaustive key searches of DES. While triple DES is regarded as secure and well understood, it is slow, especially in software. So, in a first round of evaluation, 15 proposed algorithms was accepted. A second round narrowed the field of 5 algorithms. Now, NIST completed its evaluation process and published a final standard, that is FIR-PS PUB 197, in November of 2001. This NIST selected Reindel as the proposed AES algorithm. The two researchers who developed and submitted Reindel for the AES are both cryptographers from Belgium, Dr. John Damon and Dr. Vincent Raymond. Now, the AES cipher by Reindel. This was designed by Raymond and Damon in Belgium. So this Reindel proposed for AES defined a cipher in which the block length and the key length can be independently specified to be a 128 or 192 or 256 bits. The AES specification uses the same 3 key size alternatives but limits the block length to 128 bits. So this Reindel is an academic submission based on the earlier square cipher from Belgium. Academics Dr. John Damon and Dr. Vincent Raymond. It is an iterative cipher. Iterative means that operates on entire data block in every round. So this is an iterative cipher rather than the phasal. Phasal is nothing but operating on halves at a time. So and was designed to have characteristics of resistance against all known attacks, and also the speed and code compactness on a wide range of platforms and design simplicity. So this is about the design of AES. Next, this shown is a AES encryption process, how the encryption process done. We have n rounds here, and the when the plain text passes through it, it takes as an input, and with the key blocks, it do the initial transformation, and then the state after initial transformation we get 16 bytes, and with that we'll complete the round 1. In this the same thing repeats for n rounds. So this is the overall encryption process in AES. Now coming to the AES structure, this data block of 4 columns of 4 bytes is state. Now the input to the AES encryption and decryption algorithm is a single 128-bit block depicted in FIPS PUB 197, which we discussed before. So this is as a square matrix of bytes. So the input what will be giving is in a matrix form. So this block is copied into the state array, which is modified at each state of encryption or decryption. After the final stage, the state is copied to an output. the key is expanded into 44 or 52 or 60 lots of 32 bits, which will come in the later presentation, with 4 used in each round. Note that the ordering of bytes within a matrix is by column. So, for example, if the first 4 bytes of a 128-bit plain text input to the encryption cipher occupy the first column of the N matrix, the second 4 bytes occupy the second column, and so on. Like the third 4 bytes will be occupied in the third column. Similarly, the first 4 bytes of the expanded key, which form a word, occupy the first column of the W matrix, which is taken as the another matrix here. And the data computation then consists of an add round key step. Then we have 9 or 11 or 13 rounds with all 4 steps, with the final 10th or 11th or 14th step of bytes. And plus we'll be doing the mix columns and then the round key algorithm. So this can be viewed as the alternating XOR key and scramble data bytes operations. All of the steps are easily reversed and can be efficiently implemented using XORs and the table lookups. So this is how we'll be doing the AES algorithm here. Next, the shown is the AES structure. Here this can be seen in a more detail what I explained before. This cipher consists of n rounds, where the number of rounds depends on the key length. That will be like if the 10 rounds for 16 byte key, if it is 24 byte key, then we have 12 rounds in it, and for the 32 byte key we have 14 rounds in it. So the first n-1 rounds consists of 4 distinct transformation functions, that is subbytes, shift rows, mix columns, and round key, which are described subsequently in the later presentation. The final round contains only 3 transformations, and there is an initial state transformation, add round key, before the first round, and which can be considered round 0, that is. So each transformation takes one or more 4 into 4 matrices as input and produces a 4 into 4 matrix as output. The figure shown shows that the output of each round is a 4 into 4 matrix, with the output of the final round being the ciphertext. Also, the key expansion function generates n plus 1 round keys, each of which is a distinct 4 cross 4 matrix. Each round key serves as one of the inputs to the add round key transformation in each round. So this is about the AES structure. So next, we have the subsequent steps, like, so this is one of the subsequent step in the AES structure, that is substitute bytes. Now for each of the 4 transformations used in the AES, for each stage we mentioned the forward encryption algorithm and the inverse, that is the decryption algorithm, and the rationale for the design of that stage. So this substitute byte stages uses an S box to perform a byte-to-byte substitution of the block. There is a single 8-bit wide S box used to every byte. This S box is a permutation of all 256 8-bit values. So constructed using a transformation which treats the value as polynomials in GF, that is 2 power 8. So however it is fixed, so really only need to know the table when implementing. Decryption requires the inverse of the table. These tables are given in the next presentation. So this table was designed to be resistant to no cryptanalytic attacks. Specifically, the Reindel developers sought a design that has a low correlation between input bits and output bits, with the property that the output cannot be described as a simple mathematical function of the input, with no fixed points and no opposite fixed points. So this is about the subsequent bytes, and next we have the diagram for the subsequent byte, how it is done. And next is shift rows. And this is the second stage in the AES algorithm. This is shift row stage provides a simple permutation of the data, whereas the other steps involve substitutions. Further, since the state is treated as a block of columns, it is this step which provides for diffusion of values between columns. It performs a circular rotate on each row of 0, 1, 2 and 3 places for respective rows. When decrypting, it performs the circular shifts in the opposite direction of each row. This row shifts moves at an individual byte from one column to another, which is linear distance of a multiple of 4 bytes, and ensures that the 4 bytes of one column are spread out to 4 different columns. So now next we'll see the shift rows, how it is done. This is an structure of the shift rows, how it is going on. Like for the first row there is no shifting, and for the second row we have one key shifting to the another, and for the third row we can see 2 bytes are shifting, and for the fourth row we can see the 4 bytes are shifting to the next. And this is the example below it is shown. Now next we can see the mixed columns here. For the mixed column, the forward mixed column transformation, called the mixed columns, operates on each column individually. Each byte of a column is mapped into a new value that is a function of all 4 bytes in that column. It is a substitution that makes use of arithmetic over GF, that is 2 power 8. Each byte of a column is mapped into a new value that is a function of all 4 bytes in that column. It is designed as a matrix multiplication where each byte is treated as a polynomial in 2 power 8. The inverse used for the decryption involvement as different set of constants. So this is about the mixed columns, and the shown is the mixed column structure here. And next, this is in practice, you implement mixed columns by expressing the transformation on each column as 4 equations. To compute the new bytes for that column, this computation only involves shifts, XORs and conditional XORs. For this conditional XORs will be using only for the modular reduction. And in the decryption part, the decryption computation requires the use of the inverse of the matrix, which has larger coefficients and is thus potentially a little harder and slower to implement. The designers and the AES standard provide an alternate characterization of mixed columns, which treats each column of state to be a 4-term polynomial with coefficients in 2 power 8. Each column is multiplied by a fixed polynomial a of x given in the presentation. While this is useful for analysis of the state, the matrix description is all that's required for implementation. So these coefficients will be based on the linear code with maximal distance between code words, which we discussed just now. So this is about the mixed columns, that is the third stage in the AES algorithm. Now coming to the add round key. This is the fourth stage, that is the last stage we use to do the encryption and decryption in the AES. So this add round key stage, which is a simple bitwise XOR of the current block with a portion of the expanded key. Note this is the only step which makes use of the keys and obscures the result, hence must be used at start and end of the each round, since otherwise could undo effect of other steps. So, but the other steps provide confusion or diffusion or non-linearity. That as you can look at cipher as a series of XOR with key, then scramble or permute, block repeated. This is efficient and highly secured, it is believed. This is about the add round key, and this is the structure we can see for the add round key. Now this is the AES key expansion. We'll be discussing about how the expansion is done for the AES expansion here. For the AES key. So the AES key expansion algorithm takes an input a forward that is 16-byte key, and produces a linear array of words, providing a 4-word round key for the initial add round key stage. And each of the 10 or 12 or 14 rounds which we discussed before of the cipher, it involves copying the key into the first group of 4 words and then constructing subsequent groups of 4 based on the values of the previous and fourth backwards. The first word in the each group of 4 gets special treatment with rotate plus S box plus XOR constant on the previous word before XORing the one from 4 back. In the 256-bit key or 14-round version, there is also an extra step on the middle word. Then text includes in pseudocode that describes the key expansion here. So this is the key expansion structure. The shown is here. And next we have key expansion rationalize. So the Rendell developers designed the expansion key algorithm to be resistant to no cryptanalytic attacks. It is designed to be simple to implement, but by using round constants, break symmetries, and make it much harder to deduce other key bits if just some are known. So the design criteria used are listed below. That is that includes knowing part key insufficient to find many more, or invertible transformation, and fast on wide range of CPUs, use round constants to break symmetry, and next is diffuse key bits into round keys, next is enough non-linearity to hinder analysis, and the last is simplicity of description. This is about the rationale of this key. Now next we're coming to the AES decryption. This decryption cipher is not identical to the encryption cipher. The sequence of transformations for decryption differs from that for encryption. Although the form of the key schedules for encryption and decryption is the same, this has the disadvantage that two separate software or firmware modules are needed for applications that require both encryption and decryption. This is, however, an equivalent version of the decryption algorithm that has the same structure as the encryption algorithm with the same sequence of transformations as the encryption algorithm. To achieve this equivalence, a change in key schedule is needed. So by constructing an equivalent inverse cipher with steps in same order as for encryption, we can derive a more efficient implementation. Clearly, swapping the byte substitutions and shift rows has no effect, since work just on bytes. Swapping the mix columns and add round key steps requires the inverse mix column steps to be applied to the round keys first. This makes the decryption key schedule a little more complex with this construction, but allows the use of same hardware or software for the data encryption or decryption computation. So this is about the AES decryption, and this is the structure shown for the AES decryption. And thus this is about this advanced encryption algorithm, and this is the summary. We have considered the AES selection process, the detail of Rendell, that is AES cipher, looked at the steps in each round, and next is the expansion key. So this is about this AES. Thanks.